We were discussing whether the ammonia was polar or nonpolar, and I got interrupted, so I stopped. But we had drawn the ammonia molecule with the nitrogen in the central atom. Notice that there was a lone pair, and right away we could recognize that the molecule would be polar. But we can go through a step-by-step check with electronegativity differences. We had looked up in our chart the electronegativity value for nitrogen, 3.0. Did the same for hydrogen, found it to be 2.1, and the difference between those gave us 0.9. If we stopped right here, if the electronegativity difference was 0 in these bonds, the molecule would be nonpolar. But we did find an electronegativity difference. Therefore, the bonds are indeed polar. And they're represented by that little positive sign pointing to the negative nitrogen. That the area above here with that non-bonded electron pair makes this region negative and the hydrogen slightly positive. And we use that little Greek symbols to represent partially negative and partially positive, where the electron density is being pulled to the top of the nitrogen. And again, thinking symmetry, this is an asymmetrical molecule. It results in an uncompensated polarity and therefore a net dipole moment. The word dipole means opposite poles within the same structure. A bar magnet is a dipole. Bar magnet has a positive end and a negative end. So does this molecule. It has a negative end on top of the nitrogen and positive ends here at the hydrogens. The result is a polar molecule. With that same strategy, again, we could do it the long way with electronegativity differences. We're really just thinking about symmetry. If I think about this molecule as an example, nitrogen is the central atom, oxygen and chlorine are coming off. I can see an electron domain is 3. 2 of those 3 are bonded and 1 is non-bonded. A 3-2-1 molecular geometry, 3-2-1, is a bent molecule. See the exposed electron pair on a bent molecule in 3-2-1? This molecule will be polar. Here's a molecule, sulfur with oxygen. Again, 3-3-0 is its electron domain. All 3 are bonded, 0 are non-bonded. By the way, this structure would exhibit resonance. 3-3-0 being the electron domain. So if I look this up, 3-3-0 gives us a trigonal planar geometry. Looking top, looking to the sides, all sides created equal. This molecule would be a nonpolar molecule. There's nothing unique top, bottom, or right. Remember that double bond could literally be going in any direction. We often see that shown in terms of resonance with that dashed line representing that it's really between a full single and double bond. So the length, the bond length between all oxygens are indeed equal length for that resonance structure. Symmetrical shape, nonpolar, asymmetrical shape, indeed a polar molecule. So we deduced correctly just based on symmetry. Molecular polarity affects solubility in water, and remember just this general rule, likes dissolve likes. Water is a polar molecule. Any other polar molecule will be attracted just based on charge and dissolve readily. Nonpolar molecules will not get pulled into water and will not dissolve. They are said to be immiscible. Water is polar, oil is a nonpolar long carbon chain. So you do not see oil and water mixed, just based on solubilities. So if I think about polarity as just being opposite charges, this is a bar magnet with a north and a south pole. The south pole on one bar magnet attracts the north pole of the other. Same is true for water molecules. A positive region of water will attract the negative region of another water. Again, this is just known as a hydrogen bond. So I must have charges on a particle in order to have it dissolve in water. When I flip the slide, looks like we're flipping gears. We have orbital diagrams for the formation of hydrogen sulfide. Hydrogen sulfide. We have hydrogen with a 1s1 orbital, and there's 2 of them, so I've seen 2 boxes there. Electron configuration for the valence shell only of sulfur. Sulfur who lives in group 6A, 1, 2, 3, 4, 5, 6 valence electrons. The electron pairs that are being filled with the hydrogen are going to be placed in the boxes of sulfur. So what have we just shown here? What I'm actually showing is the electron configuration of sulfur, just the valence shell. We would have written 1s2, 2s2, 2p6, 3s2, 3p4. You can clearly see the unpaired electrons in the sulfur third energy level, p sublevel. The hydrogen simply goes in with an opposite spin, creating the bond. All they're showing here really is electron domains being represented with electron configurations. The valence bond theory of hybridization. One of the issues that arises is that the number of partially filled or completely empty atomic orbitals did not predict the number of bonds or the orientation of bonds. Carbon is a prime example. Carbon, with its 2s2, 2p1, 2p1, 2p0, would predict 2 of the 3 bonds that are 90 degrees apart rather than 4 bonds that are 109.5 apart. Therefore, we are going to hybridize. I'm going to clarify with a simple example of this particular slide. Carbon lives in group 4A. When we draw a Lewis dot structure for carbon, we were taught to draw one top, bottom, left, right. 4 dots, one around each side, before you go back and give partners. What we were actually showing you is something quite advanced. It's called a hybrid orbital. Let me explain with our electron configuration. Carbon is number 6. I looked at my chart, number 6. To represent 6 electrons using our electron configuration, we would write that as 1s2, 2s2, 2p2, giving me 246 total number of electrons. And if we represent that using the orbital diagrams, either with boxes or circles or dashed lines, we would place 2 electrons in the first energy level, 2 more electrons in the second energy level, 2s2. The P have 3 different orientations. We called them px, py, pz, and we would place 2 electrons in the second sublevel of the second energy level. But what we notice is we have a completely empty orbital in the p sublevel and a filled sublevel in the s. Recognizing that it's one electron pair that needs a partner, I would suspect that only 2 bonds would form with carbon, and yet that's clearly not the observed pattern of bonding. What we do instead, and it really is just automatically what we've done up here, we promote 1 electron from the s orbital and let it have its own room, and we hybridized an orbital. Hybrid means a combination of 2 things. So truly what we're showing is 1 electron in the s sublevel and 3 electrons in the p sublevel.